Good morning, class. Today we're going to talk about rational functions. The formal definition is that r of x, and you could just as easily say f of x, it just seemed like r was a good letter for a rational function, that r of x is equal to p of x over q of x, where p and q are polynomial functions. So some examples of rational functions, the most basic one, 1 over x. You could have x plus 2, that's a polynomial, over x squared plus 3x minus 10. You could make the fancy one on top, x squared minus x minus 2 over x minus 3. You could make these have higher degrees. They could be an x to the 5th and x to the 8th. Wouldn't that be fun? You can have a really simple one where you have linear functions on the top and the bottom. I'm going to claim that this still fits this definition if I took the plus 1 and I could have a denominator of x plus 2, and then I could add them, and I would get a function that was in the form p over q. So I'm still calling this a rational function, even though it's not written in this technically specific form, because it could be written that way. We're going to talk about all of these different functions today. Alright, so let's start with the most basic of the rational functions, f of x equals 1 over x. So we're going to analyze this function, and function analysis is a big part of this section. You need to be working towards being able to analyze these functions with no calculator at all, which is terrifying, I understand, but you're going to get a lot better at it, so that's what we're learning this class. Okay, let's talk about the domain. So what values can you not plug in? Just 0, right? Okay, I'm going to put that in here. If I can't plug in 0, that probably means to us, right, that it has what at x equals 0? Hopefully a vertical asymptote, right? So I'm just going to put that in. So there is a vertical asymptote at x equals 0. Alright. Is there a y-intercept? Doesn't look like it, right? Okay, so there's no y-intercept. Let's worry about the x's for a little bit. Let's look at end behavior, because I'm not sure about range necessarily if I haven't looked at a calculator or been to an algebra 3-4 class or anyway, sorry. End behavior. So if I plug in a really big x value, like 100, right? 1 over 100. That's really close to 0. If I plug in 1 over 1,000, it's even closer to 0. So if I let the limit as x approaches infinity, if I plug in something really close to infinity, as I move towards infinity, my y values become 0. And as I plug in x values that are approaching negative infinity, let's see, 1 over negative 100. That's pretty small. 1 over negative 1,000, that's even smaller. 1 over negative 1,000,000, this is getting silly. Okay, my y values are still approaching 0, but maybe from the other side. Okay, so it looks like I have a horizontal asymptote at y equals 0. I'll draw that on the graph. This is the one at y equals 0. This is the one at x equals 0. Okay. Now, that means I can fill in my range, which was from negative infinity up to 0, and then 0 to infinity. Okay, let's look at this graph. If I plug in something like 1, I'm going to get 1. If I plug in something like 1/2, 1 over 1/2, that's going to equal, flip and multiply, it's going to equal 2, right? 1/2, 2. If I plug in 1 over 100, which is a very small number, it's over here, I'm going to get 100. Oh my goodness. Whoa, there it goes, right? Okay, here's what my graph is doing. Now if I plug in negative 1 over 100, I'm going to get negative 100, so I know this is going down here, right? Would you call this even or odd symmetry? It would be odd, right? Even, remember, is symmetric across the y-axis. Odd is rotated 180 degrees. Okay, so we've got odd symmetry. It's clearly not continuous, it has an infinite discontinuity, as many of these functions do. Perhaps all of them, we'll soon see. Intercepts, it's not going to have any here, so you don't have to worry about those. This is pretty much a full analysis of the function. So now let's make the function a little bit more complicated. So really quickly, if I wanted to take this function and perform these transformations, let's see what parts of it would change. So say I want to shift it left and right. Okay? That normally happens when you take the x value, and instead of x, you put in parentheses what? X minus something, right? It could be x minus 2, x minus 5, and if we're just working with variables, we normally say x minus h. Okay. Alright, so h values would shift left and right. Say you wanted to shift up and down. That's the one where you take your y values and you add 3, or you subtract 6, or you something like that, right? So if I take my function as it is, and I add something to it, say k, then my function is going to shift up, or it's going to shift down k units. And if I want to make the thing stretch, right? So what would happen if I took this function and wanted to stretch it? If I wanted to double it somehow, right? Stretch all my y values by a factor of 2. All I would have to do is what? Multiply by 2, right? If I multiply this by 2, say, times 2, I get 2 over x. If I multiplied it by 5, I'd get 5 over x. I would want to do this vertical stretch before I did my shift, so pretend that's not there. If I want to do a vertical stretch here, instead of 1, I'm going to put a. Multiply that function by a value. Could be 5, negative 2, 3.6, doesn't matter. And then when I add something to it, that'll move it up and down. This is true if you have a linear function over a linear function. The instant you put quadratics into this whole process, this becomes very, well, the functions are much more complicated. So as long as this is linear over linear, you're good, and it's pretty simple.